Okay, I kind of discovered something last night as I was watching YouTube videos. I probably don't watch the same Oops, let me get my microphone hooked up. All right, this probably sounds better. All right, last night I was looking at some stuff about circumcenter and all that kind of thing. Came across this YouTube video. It was a shorts video, it was like 20 seconds long, I guess. And they showed me something that I had never seen before, and I thought, wow, that's pretty interesting. And so I messed around with it on GeoGebra, and hopefully I figured it out. Thought I'd show you too. I had never heard of this before. Don't know why. Nobody taught it to me. I never saw it in a book. I never knew anything about it. But I thought it was kind of interesting. Maybe you will, maybe you won't, but I thought I'd show you anyway. Get the screen to stay on. Okay. So what I'm going to do is we're going to do that circumcenter and orthocenter, but I'm going to introduce one more thing that I wasn't going to talk about until tomorrow. I'll officially do it tomorrow, but I'll just throw it in there today, which I thought it was pretty cool. And apparently everybody on YouTube knew about it except for me. Maybe not. Maybe not everybody, but anyway, I thought it was kind of neat. So what we're going to do, this is good review anyway from what we did yesterday. Everybody's listening? Okay. So what we're going to do is we're going to do circumcenter, we're going to do orthocenter, and then I'm going to introduce a third one that, again, like I said, I'm going to talk about tomorrow. I'll do that officially, but I'll just throw it in there for today. So let me get that door, please. All right, so let's do the circumcenter. How do I find the circumcenter? How do I know where the circumcenter is on this circle? What do I do? Hypotenuse? I don't think we even said hypotenuse yesterday. Yes, the perpendicular bisector. Okay, so I'm going to click on perpendicular bisector. I'm going to click on all three of these sides. So what it's going to do, it's going to make a line that is perpendicular to that side, and it bisects that side, so it hits right there at the midpoint. Everybody good with that? All right. So I'm going to do it to this one, do it to that one, and do it to that one. And they don't just happen to, but they all intersect right there at that one particular point. And what do we call that point? The circumcenter. So let me label it. Circumcenter. So this is not anything new. It's what we did yesterday. It's just a little bit of review. Let me get rid of all those lines because they can kind of get in the way. All right. What's the second thing we did? So there's the circumcenter. And we learned something about the circumcenter. We said the circumcenter was equidistant from the vertices. Thank you very much. All right. It's equidistant from the vertices. We're not going to worry about that for what I'm showing you right now, but that's what we talked about yesterday. What was the second thing that we did yesterday? Orthocenter. How do we find the orthocenter? Give me one word. Give me one word.
Oh,
One word.
Don't answer. Altitude.
Altitude. Very good. At least it was in your notes. That's good. So the altitude. So how do we find the altitude? We go from a point, what? Perpendicular to the opposite side, right? That's the altitude. So if I go from here to here, there's the altitude. Does the altitude necessarily hit the midpoint? No, not necessarily. Sometimes it could, depending on the way your triangle is, but not all the time. But it is a right angle. See that? That's a right angle. And it goes from a point perpendicular to the opposite side. Let's do that to the other ones. Let's do it to B. So it's from here to here. See, that's perpendicular right there. Then I go from C to the opposite side, and it's perpendicular there. And guess what? It also meets at one point. We had a word for that. I didn't mention this yesterday, and I should have. We talked about this a long time ago in this class. What is it called when lines all meet at one point? They intersect, but more than that, there's another word. Those lines are Starts with a C.
Correspond.
Not corresponding. It's C-O-N.
Connect it.
That is C-N. That's C-O-N. C-O-N, but that's not the word I'm looking for. It's concurrent. Do you remember that? The lines are concurrent. Yes? No?
Yeah.
Okay. All right. That's fine. If you forget, I get it, but hopefully at least it rings a bell. So what is that point where they all meet? That's the orthocenter. I was watching a video and they were talking about the orthocenter and they said why it's named orthocenter, and now I forget. There is a name. There is a reason why it's called the orthocenter, and I just forget. What is it?
Is it related to orthodontics?
Orthodontics? Don't know. Trying to find what is what
Ortho is like dental stuff.
is it? Well, an orthodontist might be. Let's see. What's the prefix ortho mean? Let's see what Google says. Oh, it means it's straight, rectangular, or upright. So basically it means it's perpendicular, doesn't it? Everybody listening? Okay. It's straight or upright or rectangular. That's a right angle. So orthocenter is formed by right angles, isn't it? And would you agree that that's true? Yeah. That's kind of cool. All right. Let's get rid of those lines just because they kind of get in the way. I was watching some videos and man, people were putting lines everywhere. They weren't doing it necessarily with a computer program, but they were drawing it. And man, it was so confusing looking. Lines all over the place. It just looks a lot cleaner and nicer. All right, so now let's introduce something that I'm going to talk about tomorrow, but this is a sneak preview. And it is called the centroid. All right, centroid. So it kind of sounds like center, doesn't it? But then it sounds like a robot or something. This is a centroid, all right? So that's what we're going to do here. Now, the way we find the centroid is by going from a vertex to the midpoint of the opposite side. And you're like, well, wait a minute, didn't we already do that? Didn't we already go that perpendicular bisector? Is that the same thing? It's not, because the perpendicular bisector, it does bisect this side, but it's also perpendicular to this side. What we're going to do is called the median. We'll talk more about this tomorrow. I'm just going to draw it. The median goes from, let's do this, midpoint. There should be a thing. There it is, midpoint. So what I'm going to do is find the midpoint of that side, find the midpoint of this side, and find the midpoint of this side. And then what I'm going to do is draw a segment from A to the midpoint. Everybody see what you just did? I went from a vertex, okay, to the midpoint, not perpendicular this time. We did that with the orthocenter. We're just going to the midpoint this time. And watch what happens. So from A to the midpoint, from B to the midpoint, take a wild guess what's going to happen. It's not that wild of a guess. Should make sense. What do you think it's going to do? It's going to go through that point right there. See that? So that's kind of cool, isn't it? So that's three different things, three different ways we can draw lines inside of a triangle that they all meet at the same point. I think that's pretty incredible, don't you? Maybe, maybe not, I don't know. So what I'm going to do is put a point right there. We have a name for it. I said it just a minute ago. What is the name for that? Centroid. It's the centroid. It's like the center. All right, and there we go. Now, again, just to make it look a little bit nicer and cleaner, I'm going to get rid of those midpoints and the line segments that I drew to connect them, and there we go. Now, check it out. This is what's pretty cool, and it's called, there's actually a name for it. Let me write it down, text. I'll see if you know how to say this. You would think it would be Euler's line, don't you?
Euler's.
But he doesn't pronounce it like that. They pronounce it Euler. Don't know why. Forget where he's from. I looked him up and I forget. Sounds like he's probably German. Let me look him up again. Let's hammer it, okay? Let's see. where was Euler born? His name's Leonard with an H, Leonhard. I don't know if he pronounces it Leonard or Leonard or something like that. He was born in Switzerland. Family moved to the nearby suburb. I think, looks like he probably did live in Switzerland, but here we go. He was born in 1707. So it wasn't like way back. It wasn't like in Pythagoras. Like you've heard of Pythagoras, right? We talked about him. He was way back hundreds of years before Jesus was born. This guy was born in 1707. So really, he was not, it wasn't that quite long ago. Let me just look him up real quick. I know this is not that interesting, but I'll look him up anyway. He died in 1783. So United States became a country in what year? 1776. Very good. And so he actually he wasn't American, but he was on the earth when the United States was first. I don't know what word you would use. Birthed? I don't know. Okay. Declared. Okay, I guess. Anyway, so he wasn't that long ago, all right? So he lived in the same day as Washington and Ben Franklin and all those guys, okay? So that's kind of interesting. His name was Euler. He was really a famous mathematician. He's been given a lot of names for a lot of things that he's done. I can't rattle them off at the top of my head, but again, that's what I did last night. I watched all these videos. You know how you watch one video and then the next one comes up, you go down that rabbit trail. That's kind of what I was doing last night with this guy, Euler. But it's pretty cool. But check out Euler's line. I got this orthocenter, this centroid, and this circumcenter. Watch this. Look, no matter how I move the triangle, what's happening to those 3 points? Well, they probably could touch like right there. So it's not that they never touch. They're in a straight line, exactly right, okay? I even watched this video where they did a proof, an algebraic proof of this, or geometric proof, whatever you want to call it. So check this out. I'll do a segment from here to here, and watch as I move this. Oops, that's not what I wanted. I got to click off of that. Always forget. Look at that. And so the orthocenter, the circumcenter, and the center. Remember I said yesterday there's nothing special about the orthocenter? Well, it's a little bit more special now that I saw this. Okay, I didn't really discover it, but I saw people talking about it. So the orthocenter is pretty cool. So the orthocenter and the circumcenter definitely have something in common, right? They all lie on that straight line when you move your triangle around. Even if you move it like this, okay, even if it goes off the triangle, still forms a straight line, doesn't it? Here's another thing that's kind of cool about it. This will be the last thing we talk about. I don't know. Do you think that's cool? Yeah. I think it is. All right. And let's go from. What I'm doing is drawing a segment from here to here so I can measure that segment. And I'm going to get rid of that. The line. Which one is the whole line from there to? Yeah. Okay. There we go. So now watch this. So now I can click on this, and I can find the distance or the length. Oh, I can click on that first, and then I'll tell you what. Before I click on it, what do you think? There is a relationship between this from the centroid to the circumcenter, and then from the centroid to the orthocenter. There is something special about it. Any idea? It's exactly right. Exactly right. So watch. If that's 2.4, what do you think this is? Oops, there it is. Yep. Is it? Here, let me take this off. It doesn't look. looks like it, doesn't it?
Looks like
12.
like the bottom is like a third of it.
No, it's right. Look, this one, I'm measuring it with this meter stick. Okay, everybody watching? From the centroid to here is 12. Okay, and then, so this should be what? From the orthocenter to, if this is 12, this should be what? 24. Okay, and look at it. It sure is, isn't it? 24. Would you agree? For those up front, you can see. All right, so it's absolutely true. We looked at it on the meter stick, and it actually does work. It doesn't matter where I move this. Watch what happens. If I move it to here, look, if that's 5, that's 2.5. All right, so that's another relationship between there. Who would have thought that drawing perpendicular bisectors and perpendicular lines and a median going from a vertex to a midpoint, who would have thought that you do all that stuff? First of all, I thought it was kind of cool that they actually intersect each other to make those points. I thought that's kind of cool. All right, but then putting them all three together like this, and the fact that they make a straight line, I think that's kind of cool. And then on top of that, this one is twice as big as this one. And that's pretty amazing. So when I think about stuff like this, I don't want to get too philosophical or anything, but don't you believe that there has to be some kind of a designer in this world? I mean, just this stuff right here makes me think it doesn't just randomly happen. It's not like it just all happened to fall together. To me, it points to a designer, somebody that designed this, that came up in their mind, this is what's going to happen, all right? And of course, in this school, we're allowed to talk about that. So who is that designer? Who is the designer of this math? It's God, absolutely. I think there's definitely a designer. Don't ask to go to the bathroom. I'm right in the middle of something, okay? I'm on a roll. Don't want to answer, can I go to the bathroom? I really believe, and I'm not just saying this because I'm a math teacher in Christian school. I truly believe that there's little things like this in nature. I think it doesn't just happen. It's not like people came up with this stuff. They just discovered that it was true. All right, that's what happened. I think it's pretty amazing. And so in a public school, I wouldn't be able to talk about that. But I absolutely 100% believe that God is the designer of this universe. He designed us. He designed math. He designed physics. He designed this. We discovered it. Not we, me. I didn't discover anything. Okay, I'm just going by what other people show me. But people out here are really smart people. They discovered this kind of stuff. And they didn't like make it up. You understand the difference between it? Right? They're not making it. They're just discovering that it exists. And I think it exists for a reason. I don't know. I looked and looked on with videos about Euler's line, about like what the significance is, like how do people use it. I really didn't find anything like that. But I'm sure that there's something out there that will tell you what the significance of this. I mean, just the fact that all three of those, no matter how I move this triangle, and look where the centroid is every single time. Doesn't matter how I move the triangle. Where is the centroid compared to the orthocenter and the circumcenter? It's always where? It's always in between the two. Do you agree? All right, so that's kind of cool too. And it's always double, no matter how. Now that's 4.3 and 2.2. That's just because of the oh my gosh, what am I thinking of? The decimal places, the rounding, okay? The rounding of it. So you're like, well, that's not exactly double that. That should be 4.4. But if you take it out more decimal places or you stretch it out just a little bit, there you go. There's your 4.4 and your 2.2, all right? Anyway, I thought that was kind of cool. I don't know if you share my same enthusiasm, but I think it's neat. I don't think this is in the book at all. I've never seen this until last night. It just popped up on my YouTube. Well, I was looking for circumcenter and stuff like that. And then this video popped up. I watched it. It was pretty cool, I thought. What do you think? It was cool. Yeah. Okay. So this isn't really a lesson. I just thought I'd share it with you. I thought you would enjoy it. And I did record it for those who couldn't be here today. All right. enough of that. So today we are working on, what I say, 18 to 28, is that right? And if you have your homework out from last night, get that out. We'll go over those, and then you can use the rest of the time to finish up that work in class. Yes, go to the bathroom.